All right, let's just jump right in. We are talking about a topic that, makes a lot of biology students just sweat, the Krebs cycle. But listen, I promise you, by the time we're done here, it's not going to seem so scary. We're going to make this thing totally simple and, believe it or not, easy to remember.
Yup, that's the one. You probably know it by a few other names too, like the citric acid cycle or the tricarboxylic acid cycle. But whatever you call it, it has this monster reputation for being just a pain to memorize. If you've ever stared at a chart of this thing and felt completely lost, trust me, you're in good company. But that is exactly why we're doing this. The whole point here is to tear this cycle down to its bare essentials, to make it a logical, step-by-step process that actually makes sense. No more just cramming names into your brain. We're going for real understanding of one of the most vital processes happening in your body right now. So here's our game plan. We're going to hit 6 key areas. We'll start with the big why. Why does this thing even exist? Then we'll crack the code to remember all the steps. We'll walk through those 8 key moments, count up our energy payday, and then for a little drama, we'll see what happens when the whole system gets sabotaged. And finally, we'll figure out why it's a never-ending loop.
Okay, first things first. Why do our cells go through all this trouble? What is the actual point of this complicated little engine spinning away inside of us?
Now, here's a common misconception. You might think the immediate goal is to crank out a ton of ATP directly, but that's not quite right. The main job of the Krebs cycle is to harvest high-energy electrons and load them onto these special carrier molecules, NADH and FADH2. Think of them as tiny rechargeable batteries or little energy taxis, just waiting to drop off their power at the next stage. And where this happens is absolutely key. The whole show takes place inside the mitochondrial matrix. That's the very center of your cellular power plants. And that's not a coincidence at all. It's the perfect spot to pass off those loaded up energy taxis, the NADH and FADH2, to the next stage of energy production, which is happening right next door. All right, this is where the magic happens. This is the part that's going to make this whole thing feel, well, easy. Instead of trying to brute force memorize 8 ridiculously long chemical names, we're going to use a simple map, a little memory trick that'll be our guide for the whole journey.
And this is it. This one sentence is your golden ticket. Citrate is Krebs' starting substrate for making oxaloacetate. See how that works? The first letter of each word stands for one of the key molecules in the cycle, in the right order. This sentence is going to be a roadmap.
Okay, you ready? Let's take a walk through the cycle, one step at a time. We'll just follow our mnemonic and keep an eye out for where all the action, the energy harvesting and the CO2 release, actually happens. So our mnemonic starts with citrate, and that's exactly where the cycle begins. A 2-carbon molecule, called acetyl-CoA, comes in and joins up with a 4-carbon molecule that's already there, called oxaloacetate. You put them together, 2 plus 4, and you get a 6-carbon molecule, citrate. And just like that, we're off. Next up in our sentence is the word is, which stands for isocitrate. Now this step is pretty simple, really. The citrate molecule just gets a little makeover. An enzyme comes in and rearranges its atoms to turn it into an isomer of itself, isocitrate. It's basically just a prep step for the real action that's about to come. Okay, now for Krebs, where the K points us to alpha-ketoglutarate. And you really want to pay attention here because this is a big moment. This is our first real energy harvest. The isocitrate gets oxidized and 2 things happen. 1 carbon atom gets kicked out as CO2. Yep, the same stuff you're breathing out. And we load up our first energy taxi, 1 molecule of NADH. So we've gone from 6 carbons down to 5. And the word starting brings us to succinyl-CoA. This step is practically a replay of the last one. Our 5-carbon molecule gets oxidized again, and what happens? We lose another carbon as CO2, and we charge up a second NADH molecule. So now the 2 carbons we brought in at the beginning are gone, and we're down to a 4-carbon molecule. Next up, substrate stands for succinate. Now this step is super unique. It's the only part of the cycle where we make an ATP-like molecule directly. That succinyl-CoA has a really high energy bond, and when it breaks, the cell captures that energy to make 1 molecule of GTP. And GTP is basically the same thing as ATP, it's just easily converted. The word for in our mnemonic leads us to fumarate, and here we meet our other kind of energy taxi. Succinate gets oxidized, but this time the electrons are handed over to a different molecule called FAD, creating 1 FADH2. This is the one and only time we make FADH2 in the whole cycle.
Making stands for malate. This is another really simple setup step. A molecule of water is added to fumarate, and poof, it turns into malate. All this does is get the molecule into the right shape for the grand finale. And finally, the last word, oxalasoacetate. We have officially come full circle. Malate is oxidized, and in this one final energy harvesting step, we generate our third and final NADH. And what are we left with? The exact molecule we started with way back in step 1, oxalasoacetate. It's now ready and waiting to grab the next acetyl-CoA and do the whole dance all over again.
Whew, okay. We did it. We made it through one full revolution of the cycle. So let's pause for a second and just take stock. What did we actually get out of all that? What's the big energy payoff? So let's tally it up. For every single turn, we get 3 of those NADH energy taxis, 1 FADH2 taxi, and 1 GTP, which is as good as an ATP. On the flip side, we kicked out 2 molecules of carbon dioxide as waste. All that beautiful energy stored in the NADH and FADH2 is now on its way to the electron transport chain to make the real mountain of ATP. So the Krebs cycle is this beautifully efficient machine, right? But like any machine, it can be broken. And there are some pretty nasty poisons out there that can bring this whole energy factory to a screeching halt. Let's meet a couple of these metabolic villains. So let's talk about fluoroacetate. This stuff is actually in some rat poisons, and it is just nasty. What it does is it gets converted inside the cell into something that basically glues itself to the enzyme from step 2, aconitase, and just shuts it down. This creates a huge metabolic traffic jam, right? Citrate starts piling up, and the whole cycle just stops, dead in its tracks. And then you've got arsenite. It goes after the enzyme complex in step 4, blocking it. The end result for both? They pull the plug on your cell's power grid. So we've seen the steps, we've counted the energy, we've even met the bad guys. But let's wrap this up with the most important question of all. Why do we even call it a cycle? What keeps it going and going? And that, right there, is the pure elegance of the whole design. The reason it's a circle, a loop, a cycle, is because the molecule you finish with, that oxaloacetate from step 8, is the exact same one you need to start step 1. It's constantly being remade, always there, ready to pick up the next acetyl-CoA that comes along. It's a self-sustaining process, as long as the fuel keeps coming. So I want to leave you with this thought. This single, elegant cycle, spinning away in pretty much every cell in your body, is the central powerhouse for almost all life on Earth that breathes oxygen. We've seen what happens when specific poisons stop it, but just think, what does its constant, reliable turning truly mean for life as we know it?